Universal gravitation is the idea that gravity does not just act locally here on Earth, but gravity extends out into the universe. And everything with mass puts a force on everything else that has mass. And it was Sir Isaac Newton that was able to show that is true, but he built upon the ideas of Johannes Kepler. Now, Kepler in 1609 published two of his three laws of planetary motion. And he explained how the planets move, what paths they follow, but wasn't able to really explain why they do that. But he was able to show that the Earth orbits the Sun in the shape of an ellipse. And in my picture here, this axis here is twice as long as this axis here, so the ratio of those two axes is 2. If the Earth orbited in the shape of a circle, this axis would be the same as this axis, so the ratio would be just 1. Earth's orbit, the ratio is nearly 1, which means Earth's orbit is nearly circular. A lot of times you see pictures of the Earth orbiting the Sun in the shape of an ellipse, kind of like that, but that is highly exaggerated. It is true that it's an ellipse, but it's very close to a circle. So let's see what Newton was able to show here. In 1685, he published his paper on the law of universal gravitation. And what that shows is that an apple is pulled to the ground with force. Okay? Galileo was able to show that. So that's not what Newton showed. What Newton was able to show is that the force that pulls the apple to the ground is of the same nature as the force that pulls the moon into an orbit around the Earth. So the apple accelerates to the ground and the moon accelerates centripetally around the Earth. And he published that in his paper called the Principia, and very detailed paper. I'm going to show you the details as if the moon and Earth or all the planets orbit in the shape of a circle, but Newton was able to show it in the shape of an ellipse, which is much more complicated, but we won't go into that detail yet. So one of the things he said is that gravity must be diluted with distance, that the force, however strong gravity is on the surface of the Earth, must get weaker and weaker and weaker by the time it gets out to where the moon is. So Newton thought that gravity kind of spread out like light shining out as an inverse square, that however much force there was here at Earth's surface, if you went twice as far, the acceleration of gravity would be 1/4 as much, 3 times 1/9, 4 times 1/16, and Newton thought that gravity must diminish with distance. And I should point out maybe now that Newton did not attempt to say what gravity is, what causes gravity, but he was able to come up with an equation to calculate how strong gravity would be. And it does follow an inverse square law like we talked about in the last video. All right. We also talked about with projectile motion that in kinematics, that in 1 second, if an object is falling at this rate and it had 0 initial height, 0 initial velocity, and it fell for 1 second, it would fall 4.9 meters. So if you have the surface of the Earth here and an apple that is 4.9 meters above the surface of the Earth, it would take exactly 1 second for that apple to splash into the water. Okay, but we'll try to talk about how the orbit of the moon. So let's see how the orbit of an apple would be. That if you took an apple, or a laser beam I should say, and shone the laser beam out horizontally like this in a straight line, here it starts parallel to Earth's surface. By the time you get way out here, 8,000 meters away, the surface has dropped by 4.9 meters. So if you throw an apple at 8 kilometers per second, it would travel horizontally 8,000 meters in that second, but would also fall 4.9 meters in that second. It would be in orbit around the Earth. Now this is a scale picture of the Earth and Moon. Scale not only in terms of the size, the Moon is about a quarter the diameter of the Earth, but it's also in scale to the distance between these two. That the distance the Moon is from the Earth is about 60 times the radius of the Earth. So if we take the radius of the Earth and multiply it by 60, that would get us out to about where the Moon is. So right here, there's some gravity, and that's 1g. Right there, there'd be a fourth of a g, a ninth of a g, a 16th of a g, a 25th of a g, and all the way out here, gravity should be 1 over 60 squared of a g because of the inverse square law, or 1 over 3600th of the acceleration of gravity at Earth's surface. So at Earth's surface, an object would fall 4.9 meters in 1 second, but way out there at the distance of the Moon, it should fall 1/3600th of that, because that's how much weaker gravity is. Okay, and we could plug those numbers into this equation. Instead of this being the acceleration of gravity, the acceleration of gravity way out there at the distance of the Moon would be that much, and that's how I came up with this number there. That's also 1.36 millimeters. So every second, the Moon, would fall 1.36 millimeters toward the Earth. And over a course of a year or two, or a couple of years, I didn't do the calculation, the Moon should smack right into the Earth because it's falling toward it. Except it has some tangential velocity. It's just not sitting there falling straight to the Earth. It's orbiting around the Earth, and it has tangential velocity. And that's what we want to do now, is calculate what its tangential velocity should be. So I told you that the curvature of the Earth is that if you go out 8,000 meters horizontally, the surface of the Earth drops by 4.9 meters vertically. So let's calculate the curvature of the Moon's orbit in a similar way. Meaning, how far do we have to go out horizontally so that the Moon can fall that far toward the Earth, but still be on the same radius from the Earth? It's going to be falling around the Earth. So we do know that the Moon and Earth are 384 million meters apart. And if gravity were to be turned off, the Moon would travel in a straight line tangent to its path. But with gravity turned on, it's kind of arcing around like this. So we want the Moon to be able to fall this far from where it would have been, to fall from there to there, and still be at the same distance it is from the Earth. So how far that way does it need to go every second so that it can fall this far every second and still be on the same radius? Well, looks like there's a triangle there, and it's going to be a right triangle because the tangent and the radius are at right angles to each other. So we can use Pythagorean's theorem. This side squared plus this side squared should equal the hypotenuse squared. And my diagram is highly exaggerated, but this hypotenuse is a little bit longer than this side here. So if we knew what the hypotenuse was and the radius, this side here, we can find out what this other side is right here. So we're going to take the square root of the hypotenuse, which is just a little bit longer than how far it is. We're going to take the hypotenuse, square it, minus the radius squared. And then when I square root all that, the distance the Moon must travel in 1 second is 1,020 meters. Okay, this is still kind of all what the theory was, or the hypothesis was. And then let's see if the hypothesis fits with the observation. Okay, so if this is how far horizontally or tangentially it must go in a second, its tangential velocity must be 1,020 meters per second. All right, now let me ask, how much time would it take the moon to go all the way around the Earth? Well, how fast it's going is the distance it travels all the way around, the circumference, divided by the time all the way around. And I'm using a capital T here because the time to make one complete cycle is called the period, and we use a capital T for the period. So just velocity is distance divided by time. The distance that it traveled was the orbit, and then we're solving for time. If I solve that equation for time, I would get 2,360,000 seconds, and if I convert seconds into minutes, hours, and then days, I would get 27.3 days. All right, so let's just pause there and see what we've accomplished. Newton thought that gravity must diminish with distance, so he thought that it must be about 1/3600th as strong as it was at Earth's surface. Then we said, okay, how fast must it be traveling if that's true? And how much time should it take if that's true? Well, this is what we came up with, 27.3 days. From one full moon to the next full moon is not 27.3 days, but it's 29.5 days. So was Newton wrong? No, Newton was still correct. It's just the fact that not only is the moon orbiting around the Earth is orbiting around the sun. So when sun, Earth, and moon are all in line, that's a full moon. To go around the Earth one time, gets back into the upper right-hand corner, so this and this are parallel, that was one complete orbit, taking 27.3 days to do that. But to get back to a full moon, it took an extra 2.2 days to get back in line with sun, Earth, and moon. So theory says it should take 27.3 days. It takes 27.3 days. So when theory and observation match, you have a pretty good theory. All right, so Newton not only said that gravity must diminish with distance and showed that that was true based upon the time it took Earth to go around, the moon to go around the Earth, he came up with an equation to calculate how strong the force is. So we want to kind of find an equation between how far two things are apart from each other, the mass of those things, and how much force of gravity there is. We already know that the gravitational force is inversely proportional to the square of the distance. Here I'm showing the acceleration of gravity, but the force of gravity would also be proportional. Newton's second law said that the acceleration and the force are directly proportional. Okay? So the force of gravity should be proportional to 1 over the distance squared. All right? So if we had a 1 kilogram mass sitting here on Earth, there's going to be a force of 9.8 newtons on it. Okay, because 1 kilogram weighs 9.8 newtons. But if I had 2 kilograms instead of the 1, well, the force would be twice as much. That says that the gravitational force is directly proportional to how much mass there is. So just the mass of one of those things, in this case the brass mass, was proportional to how much force there was. 1 kilogram weighed 9.8, 2 kilograms, twice as much. No surprise. All right, but instead of doing it with the brass mass here at Earth's surface, let's do it with the moon way out there at some distance. Still, the gravitational force is going to be proportional to how much mass there is of that one thing. If the moon was twice as massive, well, then there'd be twice as much force between those two, as long as they're kept at the same radius. Now, if I replaced the moon with a different planet, Venus, and the mass of Venus is 66 times the mass of the moon. So 66 times as much mass right here would make the gravitational force 66 times as much. Okay? But what if this mass changed? Instead of having the mass of the Earth there, let's put the mass of Jupiter there, still keeping the centers of them the same distance apart. Jupiter is 318 times the mass of the Earth. So this is how much force there was when we just had the Earth there. But if we replace it with something 316 times as much, the force would be 318 times as much. The force would be 318 times as much. What this shows is that the gravitational force is proportional to the product of one mass and the other mass. Okay, like the first mass and the second mass. Remember, this isn't just forces between brass masses on Earth. It extends out to anything with mass. So the gravitational force is proportional to the product of how much one mass has and how much the other mass has. So these are these two ideas. Force is proportional to the product of the two masses. Force is inversely proportional to the square of the distance. You put those two ideas together and you come up with this proportionality here. That the gravitational force is proportional to the product of the two masses, but it is inversely proportional to the square of the distance. Now, if we had like a data table here in x's and y's, when x is 1, y is 3, when x is 2, y is 6, so on, y is directly proportional to x. It doesn't mean they're equal. 1 is not the same thing as 3, 2 is not equal to 6, but they are proportional. You can set them equal if you multiply by the right proportionality constant. So x multiplied by 3 would give me y. 1 times 3 is 3, 2 times 3 is 6, 3 times 3 is 9. So if one thing is proportional to another thing, we can set them equal if we multiply by the right number, some proportionality constant. And we're using big G here because big G stands for the universal gravitational constant. And Henry Cavendish in 1798 did an experiment and actually measured the universal gravitational constant, and he measured it to be 6.67 times 10 to the negative 11. A very, very small number. So you need a very, very precise instrument to be able to measure such a small number. So this is his apparatus. This is from his original drawings. I'm going to show you a more modern version of it, but this could just set on a desktop. These are steel or lead weights, and so we have these two large ones here and two small ones here. The two small masses are attached to this bar, but that bar is hanging from a tiny, tiny, tiny wire, and that wire is springy. Not just springy so it's going to stretch in length, it's going to be springy as you try to twist that wire. It will try to twist itself back. It's called a torsional wire. And there's a little mirror mounted on that apparatus so that you can shine a laser beam and you could measure very, very small angles that it twists. So let me just show you that same thing from a top view. So it starts out with these two large masses equally spaced between the two small masses. Okay, and so this has mass and that has mass. There's gravity between those two. There's gravity between those two and here and here. There's gravity between those two and there's gravity between those two. So right now everything's all balanced out. But you could shine a laser beam onto that mirror and have it bounce off onto a screen here and measure that angle. If we twist this thing around and bring them closer, now the forces of gravity are not all balanced out. There is a force of gravity I almost said pretty strong. It's exceptionally weak because you only notice the force of gravity when the mass of one of the things or the other thing is pretty large, because it's a pretty small constant there. But if he, with the two, let me show you that again. With this mass closer to here, and those masses here hanging from that tiny little wire that could twist, these are going to be allowed to twist closer to it ever so slightly. But shining a laser beam onto that mirror, the laser beam is going to deflect ever so slightly. And if we know how far one mass is from the other mass, and we know the mass of one and the mass of the other, knowing the angle that it twisted and how stiff that spring is, you can calculate how much force it would have taken to do that, which would be that gravitational force. So we know this variable. We have to know the tension in that string, that's the wire. We have to know this mass. We have to know this mass. We have to know this distance. We have to know everything in that equation except for g. And if we solve for g, we find that it is 6.67 times 10 to the negative 11. It's a very, very small number. And for that reason, we only get forces that are that we could feel if one or both of the masses are pretty large. In fact, the mass of the Earth, that's 1,000, a million, a billion, a trillion, quadrillion, pentillion, hexillion. I'm going to call that Bluhm-illion, 9.795 Bluhm-illion. That's my last name. So if you don't know what it is, just make up a name. Maybe I name it after myself. Anyway, how the heck do we know the mass of the Earth? Well, Henry Cavendish measured the mass of the Earth by measuring that number there. How did he do that? How did we know the mass of the Earth in 1798? Well, you ready for it? We put a 1 kilogram mass on the Earth. That's how we find the mass of the Earth. Do you see it? Well, we know, because we know this constant of proportionality, a 1 kilogram mass weighs 9.8 newtons, and we know the radius of the Earth as 6,378,160 meters. So we know the force on this mass. We know that it was 1 kilogram. We know how far it is. We know the proportionality constant. The only thing in the equation we don't know is the mass of the Earth. And if you solve that, you get that number there. And that's how we find the mass of the Earth. Students often ask me, well, let me come back here. Students often ask me, well, how did they know the mass of the Earth in 1790, the radius of the Earth in 1798? Well, they had known the radius of the Earth for many, many years before 1798. It was Aristarchus of Samoa that it didn't measure the radius of the Earth, but this is over 2,200 years ago. He was able to figure out that the distance between the moon and the Earth is about 1/20th the distance the sun is from the Earth. And he was able to see at the moment the moon is exactly half lit and half dark, and when it's over here, half lit, half dark, and figured that was an 87-degree angle. So this was a 3-degree angle. So using sine, opposite, and hypotenuse, he was able to calculate that this distance here was 20 times this distance there. But he did that sometime in his lifetime between 310 BCE to 230 BCE. One of the other interesting things that he said was that he observed a solar eclipse, and when the moon gets between Earth and the sun, you can see that the moon is round by looking at the shadow of that. But during a lunar eclipse, where the Earth casts its shadow onto the moon, you can see that shadow is round. So if the Earth casts a round shadow, the Earth is round. Okay, and that was known a long, long time ago. Remember, in 1492, Columbus sailed the ocean blue. People still thought the Earth was flat, not round. It was Eratosthenes of Cyrene that actually measured the radius, and this is still in BCE, over 2,200 years ago, that not only did he know the Earth was round from what Aristarchus said, he was able to measure the radius of the Earth. So he did so because in the town of Cyrene, there was a well that on one day of the year, the sun's rays would shine directly to the bottom of the well. Wouldn't do that on any other day. So the sun must have been directly overhead. He also knew that in the town of Alexandria, there was an obelisk there that on the same day when the sun was shining directly to the bottom of the well, that obelisk cast a shadow so that the obelisk was not, or the sun was not directly overhead. Okay, so the sun's rays here were shining straight toward the center of the Earth here. The obelisk was pointing straight up, so it was also in line with the radius of the Earth. Measuring this angle here would be the same as this angle there. Okay, this is pretty brilliant for so far ago. He knew that it was, the unit he used was stadia, but it works out to be about 500 miles between Cyrene and Alexandria. And knowing that that distance there was 500 miles, that is a fraction of the whole circumference. And that fraction of the whole circumference is going to be the same fraction as this angle is out of 360 degrees. So knowing that it was 500 miles, he was able to solve for the radius of the Earth. And that's pretty amazing way back when. In 1846, Uranus was orbiting the sun, and as astronomers watched it, it didn't quite follow the path that we thought it should follow. It got perturbed. It was displaced here a little bit, and it took them just a couple days to figure out what the problem was. There must have been another planet putting a force on it, pulling it out of the way, and Neptune was discovered using Newton's law of universal gravitation. So anyway, this is all just applications of Newton's law of universal gravitation. We are going to talk about orbital mechanics and gravitational fields in my next video.